The shredding of mixed post-consumer end-of-life electronic batteries results in the creation of a volume of complex residues that contain a number of different elements and metals. The need to establish a robust recycling system that is capable and able to handle any of this large range of battery chemistries may be required. In an effort to understand some of the key fundamentals that drive the waste and recycling industry, we have developed a website, waste.net, to act as a tool to assist in grasping the 4R strategy of reduce, reuse, recycle, and recover. Within the 4R's recycling sector, e-scrap battery recycling produces an ongoing generation of complex materials, such as the recovered fraction known as black mass battery residues. These residual materials consist of a dynamic blend with a changing and evolving matrix. Due to a number of continuously varying factors, determining the parameters for the requirements and infrastructure for establishing a robust recycling or recovery process is challenging. These factors may include the longevity and time span between manufacturing and end of life, an ever-changing environment of battery chemistries, and a mix of multiple manufacturers of the post-consumer battery recycling streams. With all of these dynamic factors, there is a need for a flexible and highly adaptable processing system. Some of the different types of lithium battery scrap that we see may include a mix of 1. LFP, lithium iron phosphate, referred to as LiFePO4, 2. LCO, lithium cobalt oxide, 3. LMO, lithium manganese oxide, 4. LTO, lithium titanate, referred to as Li2TiO3, 5. NCA, which is a nickel cobalt aluminum oxide, and 6. NMC, which has a nickel, manganese and cobalt chemistry. One of the most common types of lithium-ion battery that we currently encounter is the NMC chemistry. This typically contains 40% graphite, 20% nickel, 6% cobalt, 6% manganese dioxide and 3.5% lithium. While a typical dry cell or alkaline battery may contain a black powder residue that consists of 15% graphite, 30% zinc oxide and 40% manganese dioxide. The collection and shredding of any combination of these scrap batteries may produce a quantity of miscellaneous plastics and nonmetals, along with electrolytes and fringe or trace metals that may include steel, copper, aluminum and the residual material referred to as black mass battery residues. One possible scenario, as a pathway for a flexible and robust recovery process, that may process any combination of these battery chemistries, is a sequence of wet chemical or hydrometallurgy acid loops, that can separate the metallic fraction from the nonmetallic fractions. The nonmetallic fraction may be routed into the thermal reduction process for further recovery. The metallic fraction may proceed down a nitric acid leaching loop, where all of those metals that are soluble in nitric acid will dissolve into an ionic state, and be separated from any non-soluble elements. The bulk of these metals include a mix of copper, nickel, cobalt, iron, zinc and lithium. This group of items may then be subjected to a real-time analytics, and then a concentration and selective extraction stage. Any metals that are not soluble in the nitric acid loop may then be directed into a hydrochloric acid loop. After obtaining a real-time analytics, it may be confirmed that the primary elements that are soluble in HCl are manganese dioxide and any residual aluminum. The manganese dioxide with a symbol of MnO2 is dissolved into an ionic state as manganese chloride or MnCl2. The MnCl2 may be converted by displacement with aluminum, and this reaction produces a metallic manganese as an output product. Please be aware that once the metals are in an ionic state and dissolved in a solution, the option of selective extraction by electrowinning or electro-refining is an alternative choice of refining and recovery. With any of the hydrometallurgy loops, these processes are carried out and contained within an acid house and the acids are recovered in an acid waste regeneration step. We will discuss the concepts of the acid house and the acid regeneration process in greater detail at another time. Any alkali elements contained that are water-soluble may be processed in an independent loop to obtain selective extraction. These may include lithium, sodium, and potassium. The use of an electrolysis process is one option in this recovery path. In summary, We hope this quick overview of a black mass battery residue recovery system has outlined the potential to establish a recycling process capable to handle a broad range of battery chemistries. We intend to explore other types of scrap metals and residues at some point in the future. Until then, please feel free to reach out to us at your convenience. Waste.net provides a neutral platform to assist in finding a market for scrap, waste and byproducts, with the goal of matching waste material generators directly with beneficial users of those materials. By connecting market participants, we foster collaboration and promote environmental sustainability. Please feel free to visit us today at www.waste.net.